Back, everyone, and thanks for sticking with us. This is week 4 of the GMDSI notebooks tutorials, and we've been talking among the group of instructors and decided that there's enough material that we'd like to go one more week. So we're planning to, excuse me, have one last session next week, back to Monday, our normal time. Thanks for the accommodation for the holiday in the US yesterday. And so what we're hoping to do today is go through the IES work that hopefully you all ran, between last week and now, and then discuss that, and then get a start on management optimization, which will be the last, sort of the last topic that we're going to cover. So to start off, we thought we would go through the IES notebooks that you ran. So I'm just going to bring up the first one, but just wanted to open it up for questions and comments, any discussion. Like, love to get feedback on what's making sense for people, anything that's maybe not, anything that we can expand on. And barring that, there's a couple other things we wanted to cover as well. But first, I wanted to open it up and see where people are. If you could use the hand raise thing, that'd be great. And let us know what made sense, any sticking points. Josue, right? Is that the right pronunciation?
No, that's all right. It's Josue.
But Josue, right. Sorry.
It's totally cool. It's a hard one. I was confused. I sent some questions out, but I wasn't sure what the right venue, so I'll just restate them. One, I'm still confused on how does IES march through the algorithm? Is there a flow chart somewhere or a report somewhere that I can read where it says hey, this is the steps it goes through when it's running the model? Because I was just kind of confused of the overall process. And I've seen something for an example, in other GMDSI publications, there's some very simple flowcharts. It's hey, this is how pest works. Is there anything like that? And then two, I had some questions on noise, but I'll ask those later. Sorry.
Okay. Well, to the flowchart, the flowchart of kind of an individual model run is the same. So we showed an example of that early, I think in the first lesson, and I think that's in some of the other materials. The idea of writing the input files, running the model, getting the output for a single model run, right? When it comes to the actual IES algorithm, maybe we don't really have a flowchart per se, but just kind of show you an example on a response surface. So when we start out with an ensemble, if you look at the sort of the gray dots that are on this response surface, this would be a 2-parameter example where we're trying to minimize the objective function, right? We're trying to get to this kind of optimal value of the misfit between the model and field observations. So each one of these dots is representing an initial ensemble model run. And so the first thing that Pest++ has to do is run the model once per ensemble member to basically find where does it live on this surface? Where does that combination of parameters, what is the misfit or the objective function for that? And then if you're running regular pest, it would have to form the Jacobian matrix, which is a pretty expensive operation. It requires one model run per adjustable parameter. What's happening in this case in IES is it's actually using the information contained in the difference of all the parameters that are kind of all together, and the differences between the changes in observations among ensemble members to approximate the Jacobian. And the Jacobian, remember, is roughly the slope of this surface, and it's kind of pointing downhill, so to speak, toward the optimum, toward this lowest point of the objective function. And so it runs the ensemble once, it calculates this approximate Jacobian, and from that, it can kind of, for each ensemble member, it can come up with a candidate new location new set of parameters that's hopefully closer to this low point. In theory, it should always be closer to the low point. No, it's not guaranteed. And then last week we talked a little bit about this adjustment called the Marquardt lambda, where maybe that trajectory can be tweaked a little bit. That's a little bit more optimal. So there's a set of model runs to evaluate the lambda, and then that results in the next step along all of these trajectories for all these ensemble members. And then that process repeats until basically you as a user decide that you've gone far enough. And there are some metrics for that built into the algorithm. For example, if there's like no change in the number, if there's no change in the objective function in successive iterations, or if there's like no change in parameter values. But realistically, IES will probably run for quite a few iterations if you don't stop it. And we generally just stop it after a couple iterations, and kind of evaluate along that path. And that's shown a little bit also in the notebooks. So backing up, it runs the ensemble, approximates a Jacobian, comes up with a new ensemble, candidate ensemble, runs this lambda adjustment to maybe fine tune that upgrade, and then runs the next iteration of the ensemble and repeats that. Does that make sense? Is that any clearer?
Yes, no, that is helpful. Thank you.
Sure. And so I'll just say too that we talked a lot about the prior Monte Carlo and kind of the value of that. The prior Monte Carlo is just this initial evaluation of like what we know about the parameters before we run this algorithm. We are using kind of our best knowledge about the model and the kind of its place, and the properties from literature and from measurements and whatever, to come up with our best estimate of that. And it's possible that it will be like so far away from like that the modeled outputs will be so far away from the observations that this process can't work very well. And so that's one of the reasons that we talked a fair bit about rerunning that prior. That just changes where the starting locations are on this surface. And another thing that we also evaluate from the prior is how we're going to weight our ensemble, how we're going to weight the observations, and how, in addition to that weighting, how we're going to use the noise ensemble. And we could talk a little bit more about that. But that can greatly change the shape of this response surface, and that's what's shown in these notebooks. Sort of this has a pretty broad low point. It's not like super tight, and just by changing the weight on one observation, we can make that a very different shape. And in fact, in another notebook, you'll see like a big trough where they're just like correlated and there's no unique information. So so anyway, that's another thing that we're doing early in the process before we run IES. Great question. Anyone else? Yeah, German?
Herman. See, Herman.
Oh, sorry, German. Oh,
no problem.
Someday.
It's a hard one too.
I don't speak Spanish. I'm terrible.
You mentioned the weighting, and in general, in the notebook is always use the inverse of the noise as the weighting. So how the process in general change if I want to use a subjective weighting? And additional to that, what happened with regularization in PES-IS? I understand that prior information doesn't play a role directly. So how can we incorporate this, or I maybe misunderstood the things?
No, those are great questions. So first, with respect to the weighting and the inverse of the noise, that is the starting point, basically always. And if you don't specify otherwise, the PES++ algorithm will make the implicit assumption that the weights are the inverse of like standard deviation. It's in units of standard deviation, not variance. So in units of standard deviation, the errors basically. We actually, in a previous lesson, we kind of went through this idea of rebalancing the objective function. And that's where the subjectivity comes in, where, for example, a popular way to do this is looking at a pie chart of the objective function, or looking at the percentages that each observation group contributes to the objective function and rebalancing it based on knowledge we have about the system. And in that case, you can end up with weights that are not really commensurate with noise anymore. And so there is a separate column in PASS++ that you can supply, which is called, it's just called standard deviation. And we refer to it in the notebooks as noise instead of, and if that column is provided, then PASS++ will use that to sample, for each ensemble member, it will sample around the observations using that standard deviation, which is not necessarily the inverse of the weights anymore. But the weights are still used in the algorithm. So you've got two things that kind of get separated a little bit. The algorithm is still using the weights to determine kind of which misfit values contribute the most to the objective function, because that really drives the directions of the algorithm. Whereas the noise is, for each ensemble member, you're allowing the fit to be targeting a slightly different observation value. And that's really a guard against overfitting. And so one of the biggest guards against overfitting that we have is exactly that, it's the noise. And to the regularization point, that's another way that we guard against overfitting, right? Like, and if you've used PAST in the traditional GLM approach, there's a lot of discussion about regularization strategies, and that's how you're adhering to some kind of prior information. And you're right, it's not nearly as developed in IES. There are kind of some experimental ways to enforce similar regularization, but they're not as well developed. And we really rely on like sort of the covariance that you use to supply the prior. And so the samples that you make of the prior, basically, like, to cut to the chase, the prior matters a whole lot more in IES. What you start with in terms of the model structure with your prior ensemble, it plays a very important role in where you end up. And so that's yet another reason why this kind of cycling of the prior Monte Carlo is really informative and valuable, because you really want to make sure that you're starting with kind of relationships among parameters that are defensible and hopefully meaningful with respect to what you know about the system. But then we talk a little bit, like, so if you went through the notebooks, you run IES and you find, sorry, I'm just scrolling down to this point here. Oops. Well, yeah, sorry, now I'm losing it. But you started out, here we go. You started out, and what we really are interested in terms of overfitting is how well do we do representing the forecasts, right? We had these four forecasts in the model. And if we're overfitting, that means that we're probably fitting too tightly around our observations, and maybe that translates out to poor forecast correspondence. And we see that here. These aren't like terrible, but it's not great. Like this forecast is definitely certainly the peak, and most of the realizations are missing the true value. This one they're also missing. But in this case, one of the main ways to kind of underfit or to prevent overfitting is just to not go as far in the algorithm and back up to an earlier realization. And so when we do that, we can see you end up with a little bit more spread. So this is now, if you go to the earlier iteration, you end up with a little bit more spread. So you're not as confident in the results, but it does a better job not only of overlapping the truth, but also really the mode for the most likely value gets a lot closer to the truth. So this is a pretty good safeguard. And I think other forms of regularization are kind of under current development in IES, but really these are the mechanisms we have. Also SVD, which we haven't really talked about very much, you is used in the algorithm as well, and we can maybe come back to that. But I see there's a couple other questions. I'm not sure who is next here. Maybe Josue?
I think Kathleen was next.
Yeah,
Oh,
Kathleen
sorry,
was
yeah,
next.
Kathleen, go for it.
Oh, okay, thanks. My question is about how to draw the prior parameter ensemble at the end of the obs and weights notebook when you have too many parameters. But obviously I still want spatial correlation to be included.
Oh, right.
Yeah, so
Yeah.
it's more like the nuts and bolts of like how to use PyEmu to do that. Yeah, sorry, I'm a bit lost.
No, that's cool. So yeah, the issue I think that you're referring to is that if you have a ton of parameters, at some point you can't explicitly form a covariance
JCB.
matrix.
Yeah.
Right, like it just gets too big. And so yeah, the easiest way to get around that is using the spectral simulation capabilities, and it's using some other techniques. I'm pretty sure, like related to Fourier transforms, that don't have to. You can give it a geostatistical structure in the same way that you do with the covariance matrix, but you actually end up never forming the full covariance matrix. And so it uses that information and creates your ensemble, does the sampling in the way that you want to using that structure, but it just never forms that giant matrix. So in a case like that, you would need to use PyEmu to create that ensemble and then save it to a file, which it has the mechanism to do. You can save it as a compressed binary or a giant CSV file. And then you actually supply that to PES++ as an input. So PES++ will not perform that sampling. So right now, like all these examples, pretty much, we either allow PES++ to sample independent distributions for every parameter. In other words, there is no covariance. It's just like a variance for each, or we supply it with a covariance function. But yeah, like in these really highly dimensional problems like Kathleen you're bringing up, you'll need to create that ensemble external to PES++, but PyEmu has tools for that.
Okay.
And this reminds me, I don't know if you or somebody else. Oh, sweet, thanks, Katie. Yeah.
Okay.
Yeah, maybe this would be a good topic for another notebook for us to add, because this is a common problem if you have a highly dimensional problem.
And does it work? Does the spectral simulation work for an unstructured grid? Do you know? Because I did have a go at that, but
No, it has to be uniform.
It has to be uniform. Okay.
Yeah, that's the one thing that sucks for spectral. Yeah. Well, unstructured, I guess. Yeah, I'm not sure. I guess unstructured inherently. I think it requires like a uniform grid, uniform regular grid.
It does. It does. And so there would be some. I'm not sure. John Doherty with kind of his tools that he's made for some of these processes, like for sampling. There are some tricks you can do, like make a regular grid that's at the finest scale of your unstructured grid, and then up, and then sample that, and then sort of do some kind of spatial averaging to get out to the size of your blocks. And it may be that he's done a little bit of that, but I'm not sure. And there are ways that you could do that, but that could still get really expensive. I mean, presumably you're using an unstructured grid because your finest grid cells are much smaller than your largest, right? But,
yeah.
But that's
okay.
a requirement.
Maybe I'll reduce the number of parameters.
Another thing
that's
we've
an issue
done
with the math. So that's not PyEmu. Like that's just actually the mathematics of spectral simulation. So sorry, Katie.
Oh yeah, that's fine. I'll have to think about it, and we can revisit this, but you can also specify like using zones to, only do grid in that, fine grid area, and then use and I think because when you're drawing the, I'll have to check it, but I think there might be a way to actually get around it in a non-uniform grid. We've done this before with a project. But it's a good question. And one thing too is when you use that PF draw function that Mike's been talking about, so that'll build a PE is just, prior ensemble, and PF there is assuming you've named your pest from container PF. You'll want to have an extra statement after that to enforce bounds, because it'll draw and it won't necessarily actually honor the parameter bounds in your prior ensemble. So you might get some extreme values that aren't in your, parameter bounds with your prior run if you don't run that extra run that extra piece of code.
Excellent point. One other trick that you could use, depending on how your model is structured, is this is one case where pilot points may still be useful, because you could put pilot points on a regular grid and basically simulate values at the pilot points and interpolate to your unstructured grid. So that's another possibility. Cool. Josue, I guess you had a follow-up.
Yeah, mine was just another nuts and bolts question, mainly with noise. I guess two questions. One, is there a way to, we made the oe.csv file for the noise realizations. Is there a way to tell which realization of noise is being used for which, iteration of the model run? I was just trying to, I was confused of how exactly which noise realization was being used to calculate residuals or the objective function. And then two, my second question.
Go ahead.
Oh, well, and my second question, because it's related, I think they're related. I noticed the obs plus noise.csv was basically empty except for the base row. And I was trying to figure out what that file was for, because I read in the manual, it wasn't clear.
So yeah, the draws of observation noise are only made once in IES. They don't change iteration to iteration. But there's just a different set of observation values per ensemble member. And so when you read in, actually they do tie together, because if you read in that obs plus noise ensemble CSV file, it's and if you've used noise, you should see every row is a member of the ensemble. It's labeled as a member of the ensemble, and that row contains the values that are used for the observations for that ensemble member. And so if you look at one column will be one observation name, and the rows will be the different ensemble members. So if you made a histogram of that column, you would see the noise around your observed value. And so that's how you link it up. You end up linking it based on the realization name or number. And then the parameter ensemble and the observation ensemble also have an ensemble, are also indexed by the ensemble member. So you can line up all three of those things based on the ensemble, the identified ensemble member.
And so
does that make sense?
By ensemble, I think so. By ensemble, does that also mean iteration? I keep thinking to the output that has the, actual fee.csv, and it lists, the iteration as a row. By ensemble, do you mean iteration also?
No, I
okay.
don't. And so what'll happen is your obs plus noise ensemble will only have that won't change by iteration. That CSV file will be written only once. But then for your parameters, your observations, and fee, that does change by iteration. So, but what's happening is, so imagine you didn't have any noise, right? The only thing that would change per iteration is your modeled results, and the residuals would be calculated relative to the same value all the time. And so if your observation value is 10 cubic meters per second in a stream, and you've got this variety of values, each one is subtracted from 10, and you get a residual. The only difference here is that you've got a single observation value effectively for each ensemble member. And then from iteration to iteration, the modeled results change and they get subtracted from that to make residuals, but they're always subtracted from the same number throughout iterations. This is,
Okay,
yeah, there's like two directions, you know, kind of two dimensions that are happening there. Hopefully that clears it up.
I think so. Thank you.
Okay.
Yeah, and Mike's going to
reminds-
talk a bit about the base, the significance of base in that output file that you were talking about, Josue. So we will demystify the base very soon.
Yeah, I think if there's not other questions, that's actually what I was going to try to cover, and then we can move on to introducing optimization. But before that, want to make sure that everyone has a chance to ask. So wait a minute here. Sure, Herman.
Yeah, thank you. I just want to ask about observations in general, because the model has only 72 non-zero model observations, sorry. So what happens if we are using a pretty big amount? And what's how the forecasts are treated? Because there's an option where you say these are the forecasts, but as I understand the model has many other non-zero weighted observations. So how the forecast one are treated differently?
Yeah, so the forecasts behave like observations that have zero weight, because they should not be used in calculating those upgrades, right? Like they're not part of that. So so you can either just keep track in your own mind of some zero weighted observations that are meant to be forecast. If you tell Pest++ that you want certain quantities to be treated as forecasts, particularly in the GLM approach, not in IES, it does some nice calculations about uncertainty for those using the closed form FOSSM stuff that we talked about a little bit before. In IES, I think there's sort of less meaning to identifying things explicitly as forecasts. But the bottom line is they're quantities that are outputs of the model that you're going to be able to look at their uncertainty and look at their results, but they're not directly informing the actual parameter estimation process. Only the weighted observations do that. And so, you know, in a classic sense, like, you know, we often call this parameter estimation step history matching, right? Because we're trying to reproduce historical observations that we've seen in the past. Most of the time, forecasts are representing some future condition, like some kind of change in operations of wells, or, you know, something like that. And so we need to keep those separate. And really, for practical purposes, as long as they have zero weight, it doesn't really matter what how you identify them. You can decide whether you identify forecasts explicitly or not.
Yeah, I feel like it's like a bookkeeping thing. If you don't want to have to read in the massive observation ensemble to get to your forecast, then it's just a nice way to have PES like output the forecast separately. Your first question of what happens if you have lots of observations. First of all, congratulations. That's really rare, I feel like. But I mean, I think, and Mike, you can correct me if I'm wrong, just like if you have tons of parameters, relative to your number of your ensemble size, you're introducing the risk with using ensemble methods, as we talked about last week, for some of those, information from the observations to kind of pass into the wrong parameters if you have a humongous observational data set. So that's a case where you might just want to consider increasing your ensemble size, or doing some localization where you're making sure you're telling where that information should flow from your observations to your parameters. But it's generally not a bad thing to have tons of observations.
No, and in fact, like in theory, hopefully it helps. It also, just having a ton more observations helps break some of that correlation, that spurious correlation, because you've got, you're seeing the response of the model in a lot of different places, spatially or over different times, or different processes. So yeah, I agree. Congratulations. I mean, if you, it can be unwieldy to work with. That it can start to become unpractical. But we've definitely seen models running, and I've run models with like tens of thousands of observations, if we have a ton of time series, and it's a good thing generally. Awesome. Well, I didn't really prepare a slide for this, but I just kind of wanted to explain really quickly what the base realization. Oh, sorry. Actually,
Michael, yes, yeah, thanks. A small question. The gray bars are the prior probability distribution. And
yes.
My question is why it doesn't look like a normal distribution, because we have seen this before in our models, and we were wondering if we did something wrong or what. But I see the same thing here, and the question is why it doesn't looks like a normal distribution.
Yeah, that's a great question. There's a few reasons for that. One of them is if you had an infinitely large ensemble and you had a linear model, you would get all normal distributions. You should get all normal distributions for the outputs. But we've got the approximation, the fact that we don't have an infinitely large ensemble, so we're sampling it, and there are nonlinearities. There can be thresholds, right? Like classic example would be like a stream dries out or something like that. Like, so you've got this nice continuous set of values for a stream, and then suddenly it's dry.
Yeah.
Then there's no change, right?
Mm-hmm.
So basically that's what it is. I mean, these models, even this simple Freiberg model is complex enough that there are nonlinearities introduced in that relationship. So
but if we have got an ensemble with a high number of realization, it should tend to a normal distribution or not? Maybe
if it was a linear model, it would, but
okay.
Not as because the model has nonlinearities, then it's not guaranteed to be no.
So it doesn't depend of the number of realization. No?
It does a bit, but
Okay.
that would not overcome. Example, if we look at the particle time down here, right? There's one really long particle time kind of way out here.
Mm-hmm.
I mean, that's partly if you look back at the model. Oops, sorry. Do we have it? It's here. That particle is being released like right around here, and most of the time its trajectory is going along this way.
Mm-hmm.
And so that gives you kind of like, you could have a pretty normal distribution of times to get down here. But occasionally, kind of rarely, the way this model is structured, it goes actually this way around. That's why we put it here. It's right on the divide. And so that's a much, much longer travel time. And so you might get a bimodal distribution. You might end up with pretty normal, travel times around this length, but then another normal distribution around here. That's just, again, the nonlinearities of the model. So everything theoretically can be improved by a larger ensemble size, but there are limits to what that can overcome. And there are also practical limits about how much we can accommodate given our computational resources and stuff. So, at the end of the day, I wouldn't focus on that too much. I think running as big as practical, and I wouldn't be too worried about the fact that they're not perfectly normal distributions.
Okay, good to know. Thanks.
Cool. No problem.
Great questions.
Yeah, this is awesome. Thank you all for jumping in. So, when you have this ensemble, most of the time in PES++, there are cases where you don't want this, but most of the time you get something called the base realization. So you've got, like, if you make a realization of 200, you'll have 199 realizations, and then you'll have this one called the base. And basically it's the base is meant to be similar to what you would get if you ran traditional Gauss-Levenberg Marquardt. So it would be whatever your starting values were. So for example, if say this, like, hydraulic conductivity of 10 and recharge of 1.6, like this one point on this plot. If we started with that point and we ran traditional Gauss-Levenberg Marquardt, that should take some trajectory down toward the minimum, hopefully. With the ensemble, as we've kind of talked about a little bit, we're approximating that Jacobian, right? So we're coming up with a not as accurate a Jacobian, but we're coming up with some kind of a proxy that's very similar to it. If we subjected that single starting point realization and use that Jacobian, it should follow a pretty similar trajectory. That's kind of what we're arguing. But then all the rest of the ensemble is sampling the uncertainty around these parameter values. And the end result also, like as you can see, you know, in this plot, the blue, like there's a spread, like they don't all end up at the same spot, right? Like we have we retain some of that diversity or variability in the ensemble. And so, but the base realization also has another important feature, which is that it's usually more smooth. So for example, if you start out with, you know, let's say we just have 100 pilot points for hydraulic conductivity, and we're using multipliers, and we start them all at 1.0, meaning that you're not changing the base, like your kind of preconceived notion of the conductivity at all. And then you sample around that to make your ensemble. When you sample around it, some of those values are going to go higher, some are going to go lower. There's going to be a lot more noise in the ensemble. And then that noise, that relationship is going to be somewhat retained through the whole process. If one area of the field starts out higher and another starts out lower, that relationship usually isn't going to flip over in a single ensemble member. And so they're going to be a lot more noisy and a lot more variable. But the base realization, unless you tell it otherwise, it might start at all 1.0, like a smooth surface, and it's only going to bring out variability where it's indicated by this approximate Jacobian. And so the bottom line is, you know, a lot of times, as much as we've been talking about uncertainty and you know, we have all these great capabilities now in PES++ to assign uncertainty to our inputs and outputs using IES, there's still a lot of times where questions get asked and people want a single answer. And as much as, you know, we'd all like to kind of move beyond that, in a practical sense, sometimes there's value in having a single answer. And it's meant to be representative of kind of the older way, the GLM approach to solving the inversion problem or the parameter estimation problem. And so it plays that special role. It's not the mean of the ensemble. It can't be calculated from the ensemble. It's a special member that represents those starting conditions, just as if you have this efficient way to approximate the Jacobian. In PES HP, or, you know, kind of regular PES, not PES++, there's something called the randomized Jacobian, which is sort of like IES, but only reporting the base. So it's and there were some questions about that, I think, in the discussions the other week. They're very similar in the sense that base realization will probably end up in a very similar place, but that's for cases where using the ensemble is just being used as a means to an end to get a Jacobian more efficiently. But in our case, we're generally wanting both. We want to have the whole ensemble, prior and posterior. So if you run into that base realization, we don't really talk about it much in these notebooks because we're so focused on the uncertainty and those capabilities that we just haven't really, it's not something we talk about as much in the text of the notebooks. I just wanted to make sure as people see that hopefully that clears that up a little bit.
Yeah, and one example application of it, I'm working on a model calibration or history matching and uncertainty analysis for a model where, you know, prior to this, it was calibrated using GLM, Bold Pest. And so part of the task is to bring the people on board with this uncertainty analysis approach, is to first show them that, look, PES++ can still do what GLM did in terms of, you know, getting some nice looking fits to the observed data and not showing them like a, a horrifying, like, with a ton of noise, like what Mike was saying in terms of in the parameter field. It's a nice smooth parameter field, so it's very comforting, I think, for people to view. And so it's really helpful for that, because then you can say, we're really interested in not just fitting the data, but actually quantifying uncertainty in our predictions. But just so you feel comfortable with this, look at how our base is performing to, say a previous calibration or something. So I think it's a really, really handy member of the ensemble to understand. And just to add on, it's not the mean of the ensemble, it's also not the minimum fee. So you will find realizations that do better than the base in terms of the objective function.
Yeah, I've actually seen it be the lowest fee. I've seen it be the highest fee, and I've seen it be in the middle. So yeah, there's no guarantee of those behaviors. Awesome. Well, and thanks for the questions and the discussion. This is great. Oh, we got one more.
Nice.
Yeah. Hi. Thank you. I don't know if I got it right, but what you're suggesting is that it's not that good that for the starting point for the IES, I start with the lowest fee that I can find. I mean, should I go for a not that good of a calibration for a starting point?
For a starting point?
Yeah.
I'm not sure I follow, Mike. I don't. Do you?
Yeah, I mean, I think so. When you
looking at the GLM, yeah.
Right. So in other words, like if you ran GLM on a simplified version of the model and you got to some fee, like I think you're asking, would you want to use that as your starting point for IES?
Yeah.
Yeah. There are some people that like to do that. And then the idea is you're sort of starting at a pretty good point, and then you add a little bit of noise around that point, and then you're starting to characterize the uncertainty through the ensemble. The only challenge I would say is that probably if you do that, you have to do it on a simplified version of the model for computational reasons. And so you're baking in a certain amount of structure that once you make a more highly parameterized representation of the model, you might not have, that's going to change some structure. And so when you have a simplified structure, there's what we call compensatory fitting or compensatory behavior. Like maybe, for example, if you don't change recharge and the heads need to go up, and the only thing that could change is K might go really low to keep the heads up, when in reality, you wanted to decrease recharge to get the heads up. Like maybe that's like the appropriate response of the actual system. So you might end up with some kind of weird structures that you're going to kind of retain if you start at that point with IES. But nonetheless, it is also though good to as I think we've hopefully emphasized, the prior is really important in IES, and it's really good to have a well-behaved model that's not just like completely far off from, really terrible fee. So I would say that it's a possibility. The main reason that I don't do that is that I usually start out highly parameterized enough that I just don't have the computational resources to run traditional GLM first. But it's a defensible way to do it. I wouldn't say that there's a main reason not to, but you just want to make sure that you have enough variability around that starting point if you do run IES so that it can explore a range of parameters.
Oh, yeah. Thank you.
Yeah, no problem.
Awesome. All right. I guess, yeah. Is that any other questions? We're going to be moving away from uncertainty analysis and IES. All right, here we go. To another land. So this last sort of chapter of the class is all about, so we've talked about how, model inputs are uncertain, and therefore our forecasts are uncertain, and it's important to kind of explore that and quantify those. And I've certainly sat in on meetings with clients talking about this and, going on and on. And then, every now and again, somebody goes, okay, yeah, well, we know it's uncertain. Like, what do we do with that? Like, why do we care? Just being able to show somebody a histogram, it's kind of like, it's nice to look at and nice to understand, but like, how do you make a decision off of that? So this is like moving really into kind of like decision support, right? The support aspect of decision support modeling. And so optimization, or OPT, it sort of flips the script on uncertainty analysis, and it definitely requires like a cognitive reframing of the whole process. And for that reason, I think we're gonna that's why we're gonna move somewhat slowly through this and have next week's class to kind of dig more into it. But you're not thinking you're not thinking about, okay, what is the uncertainty of my forecast and how do I quantify that? Now you basically are saying, okay, our forecasts are uncertain, but I want to make a decision off of that forecast. So how do I basically optimize, some parameters to achieve an outcome, achieve a particular forecast that I want for my decision? So maybe that forecast is stream low flows, for example. And we know there's some uncertainty with respect to model inputs, and particularly pumping. So then the question with optimization becomes, okay, well, we know we want to pump, and we know that we want stream low flows to not fall below some threshold, right? So then how do we basically optimize those well pumping rates, right? So the forecast is still important. It's just that the forecast now becomes a constraint. And so moving into the kind of terminology of OPT, we've been talking about things like parameters and members or realizations of the ensemble, B, which is the objective function, things like that, right? So we're moving into the optimization land. There's new terminology. Some of them can translate over, and some of them are totally new to think about. So the first one, parameter, thankfully that doesn't change. It's an uncertain model input whose value we want to estimate and uncertainty we want to propagate through our model outputs. But then we get into what we're going to call a decision variable, which is basically something that can actually be controlled by human activity. So this is the decision support aspect. We have lots of decisions that we can make about certain operations that we can do. Say again, in the case of a stream low flow, our decision variables are well pumping rates, or they might be well locations. So things like that. And so the decision variable in like a parameter does influence important model outputs, and does have, instead of uncertainty, it has a range that it can occupy based on real world bounds for those decision variables. So for example, you can't have negative pumping. We know it's going to be 0 to some maximum amount that you can pump. But instead of it just having a prior uncertainty distribution that we have for a parameter, it has, how do I get that guy back?
Just execute the cell.
Yeah, it's weird. It's not letting me.
Really?
Strange. Yeah. Well, anyways, looks like Jupyter Lab is failing me right now. Hope everybody's okay with this text. I'll just zoom in. Yeah, so decision variable, unlike a parameter, it doesn't have just a prior uncertainty distribution. It has a range that we've said that this, decision can occupy, or can inhabit. Okay, so that's decision variable. Then we move to a constraint. And this is also a totally new thing. It's not, we don't have constraints in PES plus IES land. It's basically an uncertain model output who has a real world equivalent of undesired values. So in the case of the stream flow, again, that constraint would be a minimum threshold of stream low flows. So that would be our constraint. These are generally inequality constraints. So we basically say we want, stream flows can be above that or equal to it, but not below it. And so the homework notebooks that you guys will work through will talk about how you can actually set that up in PES. It's super simple, but you basically, identify your observations that have inequality constraints on them that now the optimization has to satisfy. And then we have the objective function. And this actually is something that's a carryover from uncertainty analysis, because everything that Mike's been talking about and with the, response service and finding this minimum, we're talking about an objective function for history matching, where that objective is to minimize the misfit, right? So we have been optimizing all along for IES. We're just trying to optimize the set of parameters that lead to, or the ensemble of members that have parameters with some amount of noise and uncertainty with them that leads to a minimum phi or objective function, right? But now in optimization land, this objective function is no longer the misfit between our observations and our simulated equivalents. It's an objective function that we are specifying, and it potentially could be nonlinear. So an example again with groundwater extraction and stream flow, our objective is to maximize the volume of groundwater extracted and then subject to not violating those constraints, right? That objective could also be, maximizing stream low flows given a certain amount of pumping, for example, too. So these are the new terminology, and it is a kind of cognitive reframing in terms of moving from a IES workflow to optimization or potentially multi-objective optimization. But it is a sort of in terms of the decision support process, it sort of follows naturally that we've quantified that uncertainty, and now we want to actually do something about it, right? Come up with reliable solutions. Okay, this is super weird. I don't know why my notebook is not running at all. Let me just restart. Here, let me do this. Some troubleshooting again. Oh, I wonder if it's because I changed the name. Okay, maybe this will work now. Oh, beautiful. Okay, cool. So I'm going to walk through a simple linear programming example. So we're going to kind of put uncertainty on hold for a second. We know it's there, and we will definitely get to it. But first, we're just going to talk about a simple example, which is linear programming. We're not looking at uncertainty. We're just looking at an objective, which is this equation right here. So basically, we are trying to maximize y, basically, or maximize z, actually, subject to x and y. And so here, our decision variables are x and y in this very simple example, right? So we have a really nice plottable kind of solution space. And then we have 5 constraints. So these are these next equations right here. And I'm going to walk through this using, this is all based on a really, really nice tutorial. And I'll put this workbook in the Reimagined Adventure repo. So yeah, we have one objective here. We have 2 decision variables, x and y, and we have 5 constraints right here. So what does that look like when we actually plot it here? It's a nice x and y plot. And basically any of the shaded areas are constraints. So we can't go into the blue, we can't go into the red, we can't go into the yellow, and they correspond to these 3 constraint equations here. And then we also have a constraint to say that both x and y have to be greater than 0. So this white area here is what we would call in optimization the kind of feasible solution space. So feasible just means that it's a solution or a set of decision variables, so an x and y value that satisfies all of the constraints. So any of these solutions satisfy the constraints. Maybe we would be happy with those, but except that we're not, because we actually want to find something that optimizes a certain condition, right? Which again was that maximizing of x and y was our objective function here. Not as simple as just simply maximizing, but something along those lines. So now we're going to walk through basically an unbounded example. And by unbounded, I mean I'm not going to set realistic bounds on our decision variables on x and y. So it would be like walking into a groundwater extraction optimization question where you're just giving some pretty outrageously wide bounds on pumping, right? So we're just saying let's let it theoretically be anything. And so what we're doing in SciPy is just basically taking all of the coefficients from the objective equation, and then the left-hand side inequality, and then the right-hand side inequality right here. And so these all just become inputs into our SciPy linear programming optimization. It's a really simple way to build it. And then these are those bounds again, they're unbounded. So we're saying they can be anywhere from 0 to infinity, X and Y. And then we run that optimization. We get our actual our objective function result here. So that's our objective result. Did we successfully find an optimal solution? Yes. And then what is the X and Y? So what are the optimal decision variables that we got? But rather than looking at those numbers, let's just plot it up. And not surprisingly, right, we're in this feasible solution space, but we want to maximize our objective. So we are up at this highest point right here in that white space. That's our optimal solution here. So that's our black dot. If we now want to try a bounded case, let's give our X and Y decision variables some realistic bounds. Now, maybe we've said, oh, you probably can only pump a certain number of, gallons per minute at these two wells. So we bring those in and we can solve it again just with those new bounds and then plot it up. Now what I'm showing you are those extra bounds in the dashed lines, as well as those colored constraints right here. And now basically we've hit up at those bounds, but we're also hitting up against the constraint here. And that's our optimal solution now, subject to those conditions. And if we go even further, we can actually show that in an optimization problem, you are either being bounded by a combination of constraints and your decision variable bounds, or your decision variable bounds are going to bound the solution entirely. And so that's what we get here. If we make 4 and 3 be the maximum for Y and X respectively, then we're not even hitting up against our constraints ever, really. We're just saying this is the optimal solution given what you could feasibly pump at those two locations. And so the main kind of thing to think about here is that hitting the constraint or decision variable bounds is now actually, it's not a bad thing, right? It's a necessity of the simplex. And this is, I didn't really get into the simplex approach, but that's basically the approach we were using to optimize these. And this is different from UA because we would potentially be concerned if our parameters were always hitting their bounds. Although Mike has mentioned that with ensembles, that's not as concerning if it's happening every now and again, or even somewhat frequently. It's just if all of them are hitting their bounds and we get that ensemble collapse that we're worried about, but that's a side point. Here, because we are trying to maximize or minimize something for our objective function, you necessarily will be hitting those bounds and walking along these bounds here. And so, for example, if you're maximizing pumping in this case, and we get these bounds on our pumping wells, then we do want to hit those bounds, and it's not a bad thing to be there because that's basically what we're saying is we want to maximize pumping and satisfy our constraints of, not depleting stream flow, which would be the colored area. So that's kind of we're at the hour mark, and that's kind of just what we wanted to get through today to get everyone kind of in the mindset of thinking about optimization, decision variables, constraints, objective functions. And then next week, we are going to kind of move more into then how does uncertainty factor into this? How could we basically incorporate uncertainty such that what we're interested in is finding the most reliable optimal solutions. So the ones that are optimal, across a given set of, parametric uncertainty. And then moving it also into MOU, which is multi-objective optimization under uncertainty, where Mike's going to be introducing the concept of, or Mike or I, the concept of a Pareto frontier. So I think I will probably just leave it there, unless if people have questions. Oh yeah.
I'll just remind that there are two notebooks, one on opt and one on MOU, that are the ones to run for next time as well.
Awesome. I think I saw a hand up, but maybe it went down. So maybe we actually ended on time today. That'd be amazing.
We can get there eventually.
Yeah, exactly. Great.
Okay, cool.
All right. Well, thanks, y'all. It was a really great discussion today.
Yeah, for sure. And we'll see people next Monday. We'll be back to Monday.
Yep. Great. Okay. See y'all.
Thank you.
Thank you. Bye.
Bye bye.